So we're going to continue with section 4.5, and we've so far looked at linear factors. In this part of the video, we're going to take a look at the nonlinear factors. We're going to look at situations in which we have quadratic factors that are irreducible, which is just kind of a fancy way of saying they can't be factored anymore. So when we look at our first example here, our function is in factored form, x plus 1 times x squared minus 10. We'll find everything we can do by hand, zeros, x and y intercepts, and end behavior, as well as the maximum number of turning points. And then we'll go ahead and use technology to get a complete graph. So as I look at this, first of all, my zeros, oops, different pen there. All right, so the zeros. We know we get that by setting our function equal to 0, and therefore we would have x plus 1 equals 0, and we would have x squared minus 10 equal to 0, right? Each factor equal to 0. This one would give us x equals negative 1. And this time, even though this is an irreducible quadratic, it's still possible to solve it, like we can solve all quadratics. And in this particular case, I'm thinking square root method. Since x squared is 10, x will be plus or minus the square root of 10. Now, since I'm going to have to put that on a graph, I'm going to go ahead and get a decimal approximation for that. That's about plus or minus 3.2. Don't need a whole lot of decimal places of accuracy there because I can only be so accurate on my graph anyway. All right, so I got 3 zeros, and notice this would have been x to the third, so it would have been a cubic or degree 3 equation. And so I can be sure I found all of my zeros. From the zeros, I know right away I can get the x-intercepts. Going to be negative 1, 0, 3.20, and negative 3.2, 0. All right, the y-intercept. Plugging in x equals 0, I'm going to end up with y equals negative 10. So 0, negative 10 is my y-intercept. My end behavior, we've already mentioned that this is going to be degree 3. So my end behavior is going to be like the y equals x cubed graph. Which I know looks like this. So we're thinking down to the left, up to the right. One thing that we added recently was the maximum number of turning points, local maximums and minimums. And since the degree is 3, that means there's 1 less, or 2 would be the most turning points we could have here. All right, let's get all this information on our graph. Let's see here. I'm definitely going by 1s on the x-axis. Negative 1, 3.2, and negative 3.2 for my x-intercepts. My y-intercept is at 0, negative 10. Just to give me a little space, I think I'm going to count by 2s on my y-axis. So 2, 4, 6, 8, 10, 20 up here. And then negative 2, 4, 6, 8, 10, negative 20 down there. There's my y-intercept. Now what I wanted to point out to you at this stage is that we could actually get a pretty good idea of what this graph looks like from here without ever even looking at our technology. We know we found all of the x-intercepts. We know we should start down to the left, so I should start down here. If I do that, I would have to come up through this first x-intercept. There's going to have to be a maximum so that I can come down through this next x-intercept. Got to come down through the y-intercept. Going to have to be a minimum somewhere in here so that I can come back up through the other x-intercept. So other than the exact location of the turning points, I have a really good idea of what this graph looks like. I'll go ahead and click over to Desmos so that we can get the slightly more exact version. But like I said, we can do a lot with just what we know. Oops. X squared minus 10. And let's see here, we'll adjust our y-axis just a little bit. And maybe, I guess I can get through there. So here are those three x-intercepts which we found. There's that y-intercept which we found. And notice, down to the left, up and back down through the x-intercepts meant there had to be a maximum there, just like we projected. And then down and back up through the other x-intercept had to be a minimum there, just like we projected. So I'm going to go ahead and label those max and mins on my graph just so that I've got them. About negative 2.2 and 6.2 be about here. And then the min at about 1.5, negative 19.4. Around there. Just gives me something to aim at when I draw. So there we are through the maximum, and we knew it was down to the left. Come down through my y-intercept, hit the minimum, and then back up through the x-intercept. So other than the exact values of the max and min, we were able to figure out all of that just by looking at our equation. All right, let's take a look at a couple of other things that can happen when we have irreducible quadratics. Here's another one. I've got a linear factor and then a quadratic factor that can't be factored anymore. So let's run through our same little list here. To get the zeros, I know I would set my function equal to 0, and so I'll set each factor equal to 0. Give me x equals 6 from the first factor, and then x squared plus 2 equals 0. If I use a square root method again, gives me x squared equals negative 2. And when I take the square root of both sides, I get x equals plus or minus. Since it's the square root of a negative, I know I'm going to have the imaginary unit there. And the square root of 2 can't be broken down any further. So I found 3 zeros, which is what I would expect, since again, this would be a third degree, right? X times x squared. Now, this is where this one gets a little bit different. What if I want to talk about the x-intercepts? Clearly 6, 0 is going to be one of them. But we can't plot these imaginary numbers on our graph. So there are no x-intercepts that correspond to that 0. 6, 0 is the only x-intercept. Only real valued zeros actually appear as x-intercepts on the graph. All right, let's go for the y-intercept. Plugging in x equals 0. Negative 6 times 2 is going to give me negative 12. So 0, negative 12. My end behavior, again, this is degree 3, as we mentioned. So end behavior is going to be like y equals x cubed. And once again, that means down to the left, up to the right. Lastly, turning points. We had the degree of 3, subtract 1, and there are at most 2 turning points. By the way, I forgot on this last one to call your attention to that when we were done. Notice last time again, degree 3 minus 1 gave us the maximum of 2 turning points, and we did indeed have 2 turning points, right? All right, let's see what happens here. Got all my analysis done. My only x-intercept is at 6, 0. My only y-intercept is 0, negative 12. And I'm going to go ahead and assume I can count by 2's again. I hope that'll work out for me here. 2, 4, 6, 8, 10, 20, negative 2, 4, 6, 8, 10, and negative 20. So my y-intercept was 0, negative 12. And that's all I got this time, right? This one might be a little bit harder to predict. We know for sure we start down to the left, and we have to go up through the y-intercept, and eventually we have to come up through the x-intercept at 6, but we don't have any other information by hand other than that. So this one we're going to have to rely a bit more on our technology. So we've got our function, x minus 6 times x squared plus 2. And you can see what happened here. There's my x-intercept at 6, my y-intercept at negative 12, and what happened was there's a maximum and a minimum, a couple of turning points that I was not able to predict this time. And the reason was those imaginary zeros, right? They didn't let me see additional zeros that turned into x-intercepts. Instead, more of the interesting stuff all happened below the x-axis. These turning points are things that I cannot predict using just algebra. I would need calculus to predict those. So when you take calculus, you'll learn exactly how to find those. For now, however, we're going to go ahead and just plot them based on our technology. There is a maximum at approximately 0.2, comma negative 11.8. And there's a minimum, and I'm going to have to go way down below where I actually labeled, so I'm going to make a few extra marks here. About negative 3, or about positive 3.8 rather, negative 36.2, approximately there. So you'll note that I put the maximum here and the minimum. I had to extend my graph down because I didn't pick a very good scale, but it happens, right? All right, so we start down to the left. We go through the y-intercept and the maximum, come down to pick up the minimum, and then go back up through our x-intercept. All right, once again, I'll remind you that we predicted at most 2 turning points, and we actually did end up seeing 2 turning points on this graph. All right, I have one more irreducible quadratic to share with you here. So here it is in factored form. I'm being a little boring here. Notice it's third degree again. But we'll start with the zeros. Either x minus 3 equals 0 or x squared minus 3x plus 5 equals 0. This one gives me x equals 3. And this time, unfortunately, I can't use the square root method, so I think I'm kind of stuck with a quadratic formula here. Opposite of b would be 3, plus or minus the square root of negative 3 squared minus 4 times 1 times 5 over 2 times 1. That's 3 plus or minus, I'm just going to do my arithmetic off to the side here. 9 minus 20 would be negative 11. So I could write that as I times the square root of 11 over 2, or 3/2 plus or minus I square root 11 over 2. So once again, as expected, with a third degree polynomial, I ended up with 3 zeros. But like we said last time, only the real valued zeros are actually x-intercepts. So my only x-intercept is the 3, 0. All right, what about the y-intercept? If I put in x equals 0, I'll get 0 minus 3 times 0 squared minus 3 times 0 plus 5. Negative 3 times 5 would be negative 15. My y-intercept is 0, negative 15. This part I know I was getting a little repetitive because we're using the same degree every time. Sorry about that. Once again, we're at degree 3. So it's like y equals x cubed, meaning down to the left and up to the right. And finally, the maximum number of turning points. Since the degree was 3, subtract 1, and that means we have at most 2 turning points. All right, so what do we know? Well, we know our x-intercept is 3. It's the only one. And I actually know my y-intercept, but I'm going to be a little smarter this time. I think I'll check the graph before I put it on here, just in case I need to change my scale. So let's see. Once again, we don't really have as much information as we'd like. We can't predict everything. Let's go ahead and check it out in Desmos. So I have x minus 3 times x squared minus 3x plus 5. And there we go. There's our 3, 0, the x-intercept that we predicted, as well as the y-intercept. And notice this time, this graph actually looks just almost like that x cubed wave, and it had no turning points at all. So I'm going to go by 2s, 2, 4, 6, 8, 10, and 20. Negative 2, 4, 6, 8, negative 10, and negative 20. I'm going to put that y-intercept on there at negative 15. And I'm just going to kind of draw what I see, right? Down to the left, comes up, there's kind of a little bit of a wave in there. And then it goes up to the right. So there's my picture of what I saw. Okay. And this time I'm going to notice that even though I could have had as many, even though I could have had as many as 2 turning points, there actually were no turning points. So that's the difficulty with these irreducible quadratic situations. We can predict x-intercepts, but usually there's not enough to help us really determine the shape. Similarly with the y-intercept, we can find it, but it's usually not enough because sometimes these graphs with irreducible quadratics will turn out to have both of the turning points, and sometimes they'll turn out not to. So these were still kind of at the mercy of Desmos to help us out with the shape. So summarizing here, can we still determine the x-intercepts by hand? Yes, absolutely, from the real valued zeros. Can we still find the y-intercept by hand? Yes, definitely, just by setting x equal to 0 as always. Is it still possible to determine end behavior by hand? Yes, it's based on the degree, right? Is it still possible to determine the turning points by hand and their general location? Finally, we have to say no. We must use technology. Because different irreducible quadratics result sometimes in different shapes, as we saw. All right, the last thing we want to learn to deal with in terms of our functions are, here we go, constant multipliers on a graph. So what we're going to do, and I'm actually going to just do this, first of all, a quick little prediction, and then we're going to go to Desmos for quite a bit of this. Notice we're going to go ahead and graph this function, x plus 2 squared times x minus 2. And then we're going to graph that same function with the multiplier of 2, 3, and 4. And we're going to do it all on the same axes. But I'd like to start by just mentioning, notice what my x-intercepts would be. I'd have a 0 at x equal negative 2 of multiplicity 2, and another 0 at x equal positive 2. So my x-intercepts would be negative 2, 0. Because of the multiplicity 2, my graph's just going to bounce off the x-axis there. And then at positive 2, 0, my graph's going to cut through the x-axis there. All of these are degree 3. And so for all of them, I'm going to expect that down to the left, up to the right. And so again, I think I can kind of predict what this is going to look like, and then we'll use Desmos to verify, right? We would go up here to negative 2, 0, bounce back down. We'll have to have a minimum in here somewhere, and then come up to the right. So up, touch, and come back down, and then cut through is what I'm expecting. One other quick thing, let's just write the y-intercept here. Notice that if I plugged in zeros, I would get 2 squared or 4. 4 times negative 2 is negative 8. Once I kind of see what I'm looking at, we'll decide how we're going to label our y-axis. All right, so first, let's put this very first function in. And notice it looks very much like what we predicted, right? Down to the left, we come up and bounce right off, just touch and bounce off that x-axis there at -2. Down through our y-intercept of -8. We knew there had to be a minimum here somewhere, and there was. And then back up through that second x-intercept at +2. Okay. I'm not going to draw anything quite yet because I'd like to go ahead and graph another version of this. We're interested in what happens if we put a multiplier, a constant multiplier, on this function. So I'm going to graph a new function, 2 times x plus 2 squared times x minus 2. And notice what happened here. My x-intercepts aren't affected at all, right? My x-intercepts are still -2 and +2. And that makes sense because this factor would still give me -2 for a 0, and that factor would still give me +2 for a 0. But it's the y values that are all doubled. Remember, this intercept was at -8. Notice in my new graph, it's -16. This minimum was at about -9.5. This minimum is at about close to -19, right? So those y values are all being doubled. We should see a similar thing happen if I put in a multiplier of 3. I'll call this one h of x. And you can see this new green graph. Once again, x-intercepts are not affected. But if we just use the y-intercept as an example, you can see that the original y-intercept of -8 has indeed been multiplied by 3. We could do it one more time with a multiplier of 4. But I don't think we'll be too surprised at what we see. Again, x-intercepts stay the same, but notice now our y-intercept is -32. Right? So if I come back to my paper, let's see, what should we do here? Let's go by 5s. 5, 10, 15, 20, 25, 30, 35, 40. My original y-intercept was at -8, so about here. And we saw that what we expected, right? We saw our graph come up and just touch and bounce off at -2. We came down here through that y-intercept and then back up through the x-intercept. My next graph, the one with the multiplier of 2, maintained the same x-intercepts, which it had to, right? The factors that we set equal to 0 are still the same. But because we doubled it, the y-intercept became 0, -16. And all of the y values in the graph, in fact, were doubled. So it looks something like that. When we tripled our original function, again we had the same x-intercepts, but all of the y values, including the y-intercept, were tripled. So now the y-intercept was 0, -24. About there. And of course, Desmos is a much prettier graph than I do, but we get the idea. And then finally, when we multiplied by 4, we still have the same x-intercepts. But all of the y values, including the y-intercept, are multiplied by 4. So we're now at 0, negative 32, about here. Like so. So that's what happens with the constant multipliers. The x-intercepts don't change, but all of the y values, which we're kind of representing by being very careful with our y-intercept, get that multiplier on them. What about negative multipliers? We already have some sense of what might happen because we've seen what happens in the shifted graphs with a negative multiplier. But let's verify. We would like to graph the original function and the original function with a negative 1 as a multiplier, a negative 2, and then a negative 4. So my original function was in red. I'm going to make this one a negative 1 as a multiplier, a negative 2 as a multiplier, and a negative 4. And you can see, compared, in fact, let me turn these two off for a moment. We'll just look at the one with the negative 1. Can you see that it's a complete reflection across the x-axis? It's literally been flipped upside down across the x-axis. And then when we add more, that blue graph gets doubled and quadrupled. So essentially the negative multiplier is going to reflect across the x-axis, which we've seen before. So again, our original, if you remember, had the zeros at negative 2 and positive 2. And let's see, I'm going to go ahead at 5, 10, 15, 20. Our original graph had a y-intercept at negative 8. And it looked something like this. Goodness, I didn't draw that very well. Let me try that little piece again. Didn't mean to make quite such a mess out of that. Kind of looked like that. Then when we got our negative multiplier, we ended up with those exact same values, but everything reflected exactly upside down, or reflected across the x-axis. So instead of negative 8, I'm going to have a positive 8 as my y-intercept. We're going to start up, come through here, have our maximum, and come down. Right, so we're reflected across the x-axis. I won't go ahead and draw these other ones because we saw them, but here we would just add a vertical stretch of 2. As well as being upside down. And here we would just add a vertical stretch of 4. As well as being upside down. All right, so let's summarize that just a bit. how does a constant multiplier affect the graph of our function? Does it change the x-intercepts? Not at all, right? Whether it was a positive or a negative multiplier, we had the same x-intercepts. Did it change the y-intercept? Yes, our y-intercepts ended up getting multiplied by whatever that constant multiplier was. Did it change the end behavior? Let's think about that for a little bit here. When we had a positive multiplier, like we did over here, notice the ends all still went down to the left and up to the right. But of course, when we had a negative multiplier, because it's flipped upside down, it did reverse the end behavior. So we need to explain this one just a little bit. A positive multiplier, we get the same end behavior. But with a negative multiplier, the end behavior reverses. All right, and then as far as any general conclusions, I just want to mention that just like we saw with the parabolas earlier, essentially when we have a multiplier, what it is a vertical stretch. Our multipliers were all bigger than 0, so we're all bigger than 1. So a multiplier greater than 1 does result in that vertical stretch, just like we saw earlier with the parabolas. I didn't give you an example, but we'll see one a little later. If I had chosen a multiplier smaller than 1, it would have been a vertical shrink or compression. Again, just like what we were seeing with the transformations earlier on. All right, so that is pretty much everything, and we are ready to put it all together. In the next few examples, we're going to try to first do everything that we can by hand, make a rough prediction of the graph, and then we'll refine it with Desmos. Right? So, we're now going to be looking at polynomial functions that are given in expanded form. We saw that we really did need the factored form in order to find the zeros. So the first thing I'm going to do is get that factored form and find those zeros. So let's see. Here with the trinomial, I'm thinking about sum and product. And since it starts out with just a 1x to the 4th, I should be able to do x squared times x squared. I'm going to need a sum of negative 18 and a product of 81. So I'm thinking negative 9 and negative 9. X squared minus 9, x squared minus 9. Now both of those are a difference of squares. So I can factor this as x times x plus 3 times minus 3. And the same for this one. X plus 3, x minus 3. Or if I wanted to be just a little bit more efficient, I could say x plus 3 squared times x minus 3 squared. All right, that would mean that my zeros are x equal negative 3, multiplicity 2, and then x equal positive 3. multiplicity 2. All right, now that we've got that, we can start answering questions. Based on the degree of the function, what do we know about our graph? Well, it's degree 4. And the leading coefficient, the multiplier, is positive. So that means it's going to have end behavior. End behavior. Like y equal x to the 4th. And it's up to the left and up to the right. Because it had a positive leading coefficient, no negative multiplier, it hasn't been turned upside down. So I'm going to stick with up to the left and up to the right. The other thing that we can tell based on the degree is the maximum number of turning points. 1 less than the degree would be 3, so we have at most 3 turning points. All right, so that's based on the degree. Based on the zeros of the function, what do we know about the graph? Well, we know that there's an x-intercept at -3, 0. And also at +3, 0. And the fact that they're both multiplicity 2 means they both are at turning points, right? They both kind of bounce off the x-axis. Because the multiplicity was 2. All right, finally, the y-intercept, we haven't calculated that, so we can do that. F of 0 is 0 to the 4th minus 18 times 0 squared plus 81 is 81. So a fairly large y-intercept of 0, 81. All right, let's see how much we can figure out about this graph. I'm going to start with a rough sketch. I know my zeros are at -3, +3. I also know my y-intercept is at 0, 81. So if I count by tens, 10, 20, 30, 40, 50, and 100, 0, 81 would be about here. I know the end behavior starts up to the right. So I have to start up to the right. When I get to the 0, I just bounce off the x-axis. I don't cut through it. I'm going to have to go up here to the y-intercept. And somewhere in here there's going to be a maximum so that I can come back down and once again bounce off the x-axis at the other x-intercept. And I end up to the right. Now, the way I have this drawn, I've got it showing, it looks like my maximum is pretty close to the y-intercept, 0, 81. Because of the symmetry in this graph, that may actually be true, although I don't know that for sure. But I think that's probably a pretty good representation of the shape of this graph. Right? And we did all that by hand, right? No technology thus far. Let's see how close we came. I'm going to go ahead and graph f of x is x to the fourth minus 18x squared plus 81. And I'd say we did a pretty good job of predicting what that was going to look like. In fact, it looks like, the maximum really is right there at the y-intercept. And we have our 0, 81 standing as both the local maximum and the y-intercept. So we can actually almost redraw that because we did a great job of predicting. Our prediction was very accurate. And in fact, the graph we found on Desmos pretty much looked like the graph that we predicted. All right, let's see how we do with another one. Our function this time is 4x cubed minus 2x to the fourth. Once again, we'll find the factored form so we can get the zeros. So in terms of factoring, I see a GCF this time, 2x cubed. When I factor that out, I'm going to get 2x. No, I'm just going to get 2, sorry. Minus x. 2 minus x, yes. So I would have x cubed equals 0, or I could even put 2x cubed equals 0 if you like. And 2 minus x equals 0. If I divide by 2, x cubed equals 0. And so I'm going to get x equals 0, but because of that third power, this one's going to have a multiplicity of 3. This one would just say 2 equal x. All right, based on the degree of the function, what do we know? It might help, and I probably should have done this before I factored because I kind of messed it up a little bit. That's okay, we fixed it. If I wrote this in descending order, it would be a little bit more obvious that the degree is 4. And this time we have a negative leading coefficient. So my end behavior is like x to the fourth, but with the negative leading coefficient, it's going to be reflected. So actually what I'm going to say is it's like y equals minus x to the fourth. Even power, so the parabola like, but upside down. Down to the left and down to the right. Based on the degree, I can also say that 1 less than the degree, or 3, is the maximum number of turning points. So at most, 3 turning points. So 2 different things you can kind of predict based on degree. End behavior and the maximum number of turning points. All right, so based on the zeros, what do we know? Well, we're going to have an x-intercept at 0, 0. And because of the multiplicity of 3, it's going to go through with kind of a wave, right? Again, if you want to be a little bit more mathematical, we could say it's an inflection point. The other x-intercept is 2, 0. And that's just multiplicity 1, so that's just going to cut straight through. And this was because of the multiplicity of 3, and this was because it only had a multiplicity of 1. Oh, sorry, couldn't see that last bit. So again, 0, 0, because it was multiplicity 3, cuts through with that wave. We call it an inflection point. 2, 0 only had multiplicity 1, so that's just going to kind of cut straight through. No wave, no bounce off, just straight through. All right, finally the y-intercept. If I plug 0 in for x, I'm going to get 4 times 0 cubed minus 2 times 0 to the 4th. That's just 0 minus 0, or 0. So my y-intercept is 0, 0. When you have an x-intercept at 0, 0, you pretty much have to have a y-intercept at 0, 0 as well. All right, so let's see what we can get from this. My rough sketch, x equals 0, my first x-intercept, x equals 2, my other one. And the only other thing I know about intercepts is the y-intercept is also 0, 0. All right, I start down to the left. Now, at the 0, 0, I probably already messed up. I really should be going through with a little bit of a wave, right? Because it was supposed to be a inflection point or a wave here. Let me draw that a little bit differently. It's going to cut through, but there's that bit of a wave that I would expect to see. Now I'm going to have some kind of a maximum so I can come back down and cut back through here at the 2, and then it goes down to the right. So I'm thinking this overall is the look that we're going for. Cuts through at 0 with an inflection point or a little wave, and then straight down through the 2. Let's see what Desmos has to say about it. So we had 4x cubed minus 2x to the 4th. And actually not bad, right? I've got a pretty big y-axis here. I can make it a little bit less. There we go. That's pretty close to what we saw. Now, I had no idea where to put this maximum. Turns out it's at 1.5, 3.375. So I could add that on my next graph. 0.5, 1, 2, 3.375. I just plotted the maximum on my graph. But other than that, we did a really good job of predicting. We see that little wave or inflection point at 0, 0. And we see that graph coming straight through at 2, 0. So I just added the correct maximum here. It was 1.5, 3.9, I think. And I could go ahead and adjust just a little bit to show that correct maximum. But really, all I would have had to have done was change the scale on my first prediction, and we did pretty well. Right? So it's just amazing what you can predict, even without knowing exactly where the maximum is. All right, I believe I have one more. So this time we're looking at a 5th degree polynomial. And I want to first find the factored form, really important if we're going to try and graph. And I'm looking at this, and I believe I could factor out a GCF of x squared before I do anything else. So let's start with that. That's going to leave us x cubed minus 4x squared plus x minus 4. Inside my parentheses here I have 4 terms, which means I should factor by grouping. So I'll keep my x squared. And then in this pair I can factor out an x squared times x minus 4. Plus in this pair I can just factor out a 1. So also times x minus 4. And I have x squared times x squared plus 1 times x minus 4. So either x squared equals 0, x squared plus 1 equals 0, or x minus 4 equals 0. This is going to give me x equals 0 because of the square multiplicity 2. This is going to give me x squared equals negative 1. So when I use my square root method on that, I'm going to get x equals plus or minus I. And over here I'm going to get x equal 4. Just double checking, notice with a 5th degree I do get 5 zeros if I count multiplicity, right? 2 here, 3, 4 with the plus and minus, and 5 over there. So I found all 5 zeros that I know this function had to have, but they're not all x-intercepts, right? The imaginary ones will not give us x-intercepts. We'll note that a little bit further down. All right, so this function was degree 5, and it's a positive 1, x to the 5th, so it has a positive leading coefficient. So I expect the end behavior to be like y equal x to the 5th. So all odd power functions have that sort of a wave shape. It'll be down to the left and up to the right. One less than the 5, so at most 4 turning points. So again, 2 basic things you can predict based on the degree. What will the end behavior look like, and the maximum number of turning points. All right, based on the zeros, what do we know about the graph? Well, x equals 0 is going to give us an x-intercept at 0, 0. And with the multiplicity 2, that one's just going to kind of bounce off the x-axis like all even multiplicities do. The imaginary zeros do not give me any x-intercepts, but I'll have another one at 4, 0. And since that one's just a multiplicity of 1, the graph's going to cut through the x-axis, kind of straight. All right, finally the y-intercept. I already really know it because with the x-intercept of 0, 0, that has to be the y-intercept as well. But I'll just for completeness say, if I calculated f of 0, plugging in 0 to my x, I'd get 0 to the 5th minus 4 times 0 to the 4th plus 0 cubed minus 4 times 0 squared, and those are all just zeros. So unsurprisingly, I get 0, 0 as my y-intercept. All right, let's put it all in a graph. Here's my rough sketch. I have 0, 0, which I know is going to be just a bounce-off point. I have 4, 0, where the graph's going to cut through. I know the graph goes down to the left. It has to bounce off here at the 0, 0. And then it can go down and come back up and go up to the right. This is certainly a possible graph, but I have I'm less sure about this graph than I was about the others, and here's why. Did you notice in my factored form that I have an irreducible quadratic, right? I was not able to factor this down into entirely linear factors. I had this irreducible quadratic. And you remember in our, when we were trial and error, doing a little trial and error, those were the ones that were the most unpredictable. It's certainly possible that I've basically got a graph that looks like this, but it's also possible that this graph, maybe had another max or a min down here. I've only found 2 turning points, and it could have had as many as 4. So it's possible it did something else in here, or maybe even over here, right? Could have come up and down and up again that I'm not seeing, and it's that irreducible quadratic that may have caused it. So I'm the least sure about this graph as I am about any that we've graphed so far. Those are the ones that are toughest to predict with what we know. But let's check. Our function was x to the 5th minus 4x to the 4th plus x cubed minus 4x squared. Okay, and it looks like I mostly got it. There's more of a flattening here at that turning point than I really drew, and it's slightly sharper, and of course it's way down here. It's all the way down at 3.2 comma negative 92 something. The overall shape we did a decent job of predicting, but there could have been more to it. We were a little bit lucky this time. So I'm just going to add this additional information. We knew our 2 x-intercepts. I'm going to go down by, let's see, I'll go by 20s, 20, 40, 60, 80, negative 100. And I'm going to put that turning point at about 3.2, negative 92, roughly here. And I'm just trying to sketch what I see now. I'm going to make that somewhat flatter turning point, and then that sharper turn at the minimum. So there's a little bit better picture of my graph. Again, we didn't do a terrible job, but there was a little bit more going on there than we could predict super accurately.